What about me? I like that Pisces, I guess. Pisces. Yeah, I'm an old man. You notice today that, see, can you see my my scout jacket? How many of you cannot wait for season 4? See, I can't wait for season 4. Forget about it. We are wasting too much time already. All right, I'm going to switch off my. I'm going to switch off my my video now. How do I do that? There. All right. Never mind. Don't spoil the movie for me. For those of you who watch manga or whatever, I'm still waiting for season 4 to come. All right. So today, yesterday we talk about Roth stability criterion. We can determine whether the system is stable or not by constructing the Roth table, but we don't know the exact location of the roots. In fact, if we know the exact location of the roots, we can actually determine how the system is going to behave, rather than just knowing whether the system is stable or not. Okay, today we are going to learn the root locus method. The root locus method allows us to trace the location of all roots on the complex plane as one of the parameter varies from 0 to infinity. Normally, we are going to vary the proportional controller. So in that case, this root locus method is quite important. I have written some notes on this. You can read. Let's go to my notes. I also uploaded this note on your e-learning. You don't have to copy anything. So it says here, a root stability criterion cannot provide the exact value of the roots of the characteristic equation. We can only know whether the system is stable or not, whether there exists a positive root or not. Root locus method gives the exact location of all roots on the complex plane. So that is more important information that we can have. From the location of the roots, we can determine the performance of a control system. The exact performance of control system will depend on the location of the roots on the complex plane. So how do we do that? How do we trace out the location of the roots of the characteristic equation? So let us consider this closed loop block diagram. So here G is the system that we want to control. H is the feedback gain or feedback transfer function, and K is the proportional controller gain. In this case, we assume that we just use the proportional controller, which is our action is proportional to the error. So consider this general closed loop system. So the characteristic equation is the denominator of the transfer function equals 0, which is 1 plus kgh equals 0. So this is what we call the characteristic equation, the denominator of the transfer function. So the roots of this characteristic equation, depending on the order of the system, if the system is third order, we are going to have 3 roots. If we trace out the roots for all value of k from 0 to infinity, we are going to have 3 paths. We can trace out the path taken by the roots as k varies from 0 to infinity. K here is our design parameter. It is the controller gain. We have seen that yesterday. for some system, when k become very large, the system become more and more unstable. So root locus method will tell us the location of the root when k varies from 0 to infinity. So it says here the root locus is the path of all roots traced out in the complex plane when the parameter k here is the proportional controller, is varied from 0 to infinity. And then here the expression kgh, alone, this, see, the characteristic equation is 1 plus kgh is equal to 0. But the expression kgh alone is known as the open loop transfer function. Okay? Kgh is known as the open loop transfer function. So 1 plus the open loop transfer function is equal to 0. This expression is in the form of complex variable s. So on a complex plane, a complex number will have what we call this magnitude and angle. If you remember correctly, when you learn about complex number, you can represent complex number in terms of the real part and imaginary part. Alternatively, you can present the complex number in terms of their magnitude and their angle. So if you look closely at the characteristic equation, so kgh here is going to be equal to -1. So on complex plane, so we can say that every point on the locus must satisfy that the magnitude of kgh must be equal to 1. Kgh is a function of a complex variable s. So every point on the locus must satisfy these two criterion. One is the magnitude criterion. The magnitude of kgh must equal to 1. And the angle of 1 is, no, it's not the angle of 1, the angle of -1. Okay, if you go back here, so kgh is equal to -1. So the angle of -1 is, of course, plus and minus 180 degrees. Okay, so these two criterion must always be met when we trace out the roots of the characteristic equation. Now, let me refresh you a little bit about this complex number. So a complex number consists of the real part, a plus, and you have the imaginary part. A is the real part, b is the imaginary part. So graphically, you can present that this is a point x. A is the real part, b is the imaginary part. The magnitude is given by this, the distance from the origin to the point. You can use the Pythagoras theorem to compute the magnitude of a complex number. And the angle here, you can use the arctangent. So the angle of a complex number is given by the arctangent of the imaginary part divided by the real part. So you can present a complex number in terms of real and imaginary part. Alternatively, you can present a complex number in terms of magnitude and its angle. So the magnitude of the open loop transfer function must always be 1, and the angle for any value of s that satisfy the characteristic equation must be either plus and minus 180. So the angle on the real axis, the angle here is 0. If you go around the clockwise, anti-clockwise, so you go here is 90 degrees, 180, 270, and 360. If you go clockwise, the angle starts at 0 on the real axis. If you go clockwise, here is -80, -180, -270, and -360. So that is why this plus and minus sign comes from. So that is the two a criterion that you must always meet when you draw the root locus diagram. And then we can interpret the behavior of the system in terms of stability after we have drawn that. So when we draw all the location of the roots, for stability, we want all roots to be on the left-hand side of this imaginary axis. It doesn't matter how many, as long as all roots lies on the left of imaginary axis, then we say that the system is stable. At the moment, we are just going to talk about whether the system is stable or not. Later on, when we have drawn the root locus diagram, then what? Then we can now interpret the time response of the system just from the location of the roots of the system. For a short discussion here, okay. So we have noticed that the further away the roots from the imaginary axis, the stable the system becomes. The closer the root to imaginary axis, the less and less stable the system becomes. Sometimes people refer that the further away the roots are, they call it the non-dominant root, the root that has no influence, not the roots that have no significant influence on the behavior of the system. So the behavior of the system we just approximate with the dominant roots. The dominant roots are the roots that is closer to the imaginary axis. You don't want the root to go to the right of the imaginary axis because now the system will become unstable. So there is some a brief interpretation of what the root locus diagram is going to tell us, how the system is going to behave. But the more detailed interpretation of root locus diagram, we will save that for a later date. So today we are just going to draw one simple root locus diagram, I guess, example 3.9. Okay, 3.9. Okay, so here it says draw the locus of the roots of the characteristic equation of the control system shown below when k varies from 0 to infinity. So this is a second order system. So we want to trace out the location of the roots when k varies from 0 to infinity. So in this case, we are going to have two roots, and all for any value of k, we are going to have two roots. So we are going to, the root locus diagram is the path taken by each root when k varies from 0 to infinity. So your first task is, of course, obtain the characteristic equation and get the expression for computation of each root. Let's go back to my notes. Okay, so this is the system, the closed loop system that we want to draw the root locus diagram of. Your first step is always obtain the characteristic equation. Characteristic equation is 1 plus kgh, 1 plus the open loop transfer function. So the open loop transfer function is k divided by s plus 2, since the feedback path is just, the feedback gain is 1, h is equal to 1. So this is the characteristic equation, and then we can expand that in terms of polynomial. It so happens that this is just a quadratic equation. Everybody can obtain the roots of this quadratic equation, second order. So we can now use the solution of quadratic equation to get the two roots, the expression for the two roots. So this is just minus b plus and minus b squared minus 4ac divided by 2a. Wait a minute. Yeah, that's right. B square plus and minus square root of B square minus 4 is, wait a minute. Why is this plus? See, there's a mistake there. There's a mistake there. There should be minus. This should be minus. Negative b plus b squared minus 4ac, not plus. Can make a correction there. So this should be minus. This is correct. The minus there is correct. Okay, that is wrong. So and then we can simplify that. Minus 1 plus square root of 1 minus k, and then minus 1 minus square root of 1 minus k. So now k is going to, we are going to vary k from 0 to infinity, and we want to compute the roots s1 and s2. Make that correction. This should be minus. See, this old man still has a sharp mind. When he or she, when I see a mistake, I can spot a mistake. Bad news for you, because when I see your answer, then I can know whether you make a mistake or not. I have a very sharp eye, I guess. Now we are going to vary this. We are going to vary this k from 0 to infinity, and then we can now evaluate each of the root. Okay, so this is the first root. Start from when k is equal to 0. So you just substitute k equals 0. So negative 1 plus 1 is 0. Substitute k is equal to 1. Okay. 1 minus 1 is 0. Wait a minute. What the hell am I talking about? So when k is equal to 0, yeah, when k is equal to 0, minus 1 plus 1 is 0. When k is equal to 1, minus 1 is 0. So square root of 0 is 0, so you get negative 1. But when k is equal to 2, the roots now become complex. The root now become complex. Similarly, you keep increasing k from 0 to infinity, but the real part here is always negative 1. Only the imaginary part will now change. And then you compute S2 when k varies from 0 to infinity as well. But here now, when k is equal to 0, negative 1 minus 1, you get negative 2. When k is equal to 1, 1 minus 1 is 0, so you get negative 1. And then the roots now become complex. So this is the point. This is the path taken by the first root, which is S1. And this is the point on the path taken by S2. And then you can trace out. You can trace out the path taken by S1 and the path taken by S2. Okay, so you start with for k is equal to 0. So this is the value of S1, and this is the value of S2. Okay. So S1 start at 0, S2 start at negative 2. S1 start at 0, S2 start at negative 2. Let us just first trace the S1, the first path. So it starts at 0 until k is equal to 2. Until k is equal to 1, the roots are still real number. When k is greater than 1, it is already become a complex number, a complex root. Okay. From k is equal to 0 to 1, the roots are still real number, 0, negative 0.5, negative 1. When k is greater than 1, the roots now become complex. Okay, so you trace that out, up to infinity. So there is the path taken by the first root. And finally, you can now trace the second root. Now we can now we have a complete root locus diagram. So this is a path taken by the S1 when k varies from 0 to infinity, and this is the path taken by the second root when k is equal to 0 to infinity. And you can see that the root locus starts at the value of the pole. Pole here, we have two poles, one pole at 0 and one pole at -2. So basically, this is what the root locus diagram is. The path taken by each root on the complex plane. I guess that's it. Do you have any question? Nine. There is another characteristic of root locus diagram. So it says here that when k is equal to 0, the locus starts at the pole of the open loop transfer function, and the locus ends at 0 of the open loop transfer function when k is equal to infinity. So the locus will start at the pole, and the locus will end at 0. So what is the pole and what is the 0? When you write the open loop transfer function, okay, so when you obtain your open loop transfer function, and then you can factor out the numerator and the denominator. The value of, if you look in the numerator, the value of s that will make the numerator 0, that is called the 0. The value of s that will make the numerator 0 is called the pole. Let me explain that using my whiteboard. It will be much better. Okay, now imagine now this is our open loop transfer function in a form of this numerator and denominator. The zeros are the value of s that will make the numerator equal 0. zeros. So zeros is a special name given to the value of s that will make the value of the numerator equal 0. There's always a confusion here. See, there is a 0. there's a 0. The name given by the value of s that will make the numerator equal to this 0 is known as the zeros. What the hell is going on? I don't know. And then the poles are okay. I see that some of you like my outfit. I do too. You see that probably when there is a fire in the building, the first thing that I grab is this jacket to save this jacket. Probably my most valuable possession here. I forget about it. So first, you need to distinguish between zeros. I always put s there with 0. 0 here is the value of 0. And the name is given by the value of s that will make the numerator 0 is called zeros. The value of s that will make the denominator 0 is called the poles. So that is what we mean by zeros and poles. So the root locus will start at the pole and it will end at 0. The root locus will start at zeros. So the locus will start at the pole and the locus will end at 0. There. It can be seen that the values of the roots of characteristic equation will change when the value of parameter k is changed. So now this is where the statement is. When k is equal to 0, the locus starts at the pole of the open loop transfer function and the locus end at 0 and the locus end at zeros of the open loop transfer function when k is equal to infinity. So how much is this? This jacket is given as a present to me. Somebody gave a present to me. My son gave it to me. They bought it online. I don't know where he bought it. I got this jacket. I really cherish this. I get distracted today, so yeah, I cannot focus on my lecture. It's all over the place. All right, so let's do this. So for a control system shown below, show that the roots start at the poles of the open loop transfer function and end at 0 of the open loop transfer function. So we are going to show here that, where is it? No, the diagram is wrong. Example. there is a mistake in the question there. See, example 3.10, it should have k, s plus 1, s plus 2. Make a correction there. There's a mistake there. All right, so first we get the open loop transfer function. Okay. From the open loop transfer function, we can see that we have one zeros at -1, and then we have two poles, one at 0, one at -2. So the zeros is the value of s that will make the numerator equal 0. Poles are the value of s that will make the denominator equal 0. So we want to show that the locus start at the pole and end at 0. Again, since this is just a quadratic equation, then we can solve for s1 and s2. So we want to show that when k is equal to 0, s1 and s2 is equal to value of the pole, which is 0 and -2. See, it can be shown that when k is equal to 0, s1, s2 is equal to 0 and -2, so it starts at the pole. 0 and -2 are the value of the poles. And since we only have one 0 at -1, only one locus will end at 0, and the other one will go all the way to infinity. Only one of the locus will end at 0, because we only have 1 0 at -1. The confusion comes from distinguishing between the value of the numerical value of 0 and the name given to the value of the root when the numerator is equal to 0. So these zeros, I always put S to distinguish between the numerical value of 0 and the name given to the value of S that will make the numerator, the value of numerator become 0. So we have shown here that the locus start at the pole of -2 and 0, and one of them end at 0 at -1. I know that my lecture is all over the place today. I got distracted with this iCat thing. By the way, I think we stop our class here today. If you have any question, then of course you can ask question in our group chat, and I guess I'll see you again next week. Probably I will wear my Star Wars T-shirt back then next week. How about that? All right, I'll see you next week.